Okay, so let's start. So good afternoon, everybody. So last time I started to explain binary others and subtractor. So here, what I'm teaching is how can you make a hardware circuit? This hardware circuit can do addition and subtraction operations. Is that okay? And all what I did here, I started with what we call half other. And you will understand. I already explained why we call it half. Okay, you will understand. But I'm gonna say it again now. But for now, this half other is actually used to add bit to bit. So if you have 2 bits, okay, only 2 bits, something very simple, because we're gonna start from something simple and then we're gonna complicate it as you will see. Okay? So I started with something very simple. I have 2 bits here, x and y. I want to add these 2 bits, and when you add 2 bits, you are gonna get summation and carry. And similar to what we did in chapter number 3, you have to make a truth table this way, and then you have this is the carry, and this is the summation, and then based on that, this is the circuit. If you use this circuit can do the addition. Is that okay? That's why this is how the circuit looks like. Okay, summation and carry. And also we can implement, because if you look at this one, if you look at the summation here, as I said last time, if you look at the summation here, this one, xy prime or x prime y, what is this? This is XOR, right? So that's why you can implement it this way, or it's the same thing if you can just implement it using XOR. So this one is okay. This one also is okay. Now, what if I wanna add 2 bits to 2 bits? 2 bits to 2 bits. Okay? The very naive idea is we can do something like that. You can make a truth table this way, okay? And then here I'm gonna add these 2 bits to these 2 bits. You can do the addition, and this is after that you are gonna get the summation of this one. You can make a truth table this way, and then you can make a circuit similar to what I did before. However, this is usually the traditional way we're going to use to design any logic circuit. Okay. However, this way is inefficient if we have too many inputs. Okay. And it may be okay for 2 if you add 2 to 2. Okay. If you add two numbers, in this case you have 4 inputs. What if, that's what I'm explaining here. For example, what if I wanna make other for 4 bits and 4 bits, add 4 bits to 4 bits. In this case, so now I'm gonna have, look how many different combinations I'm gonna have here. 256. What if the other is 5 bits? I'm gonna have the truth table is gonna be too big, right? That's why it's not gonna be efficient to do this way. What if you want to add 16 bits to 16 bits? It's going to be too crazy, right? It's going to be too big. We don't do it this way. So we're going to do it in a more efficient way. So the more efficient way is, as I explained last time, look here the idea before I explain all of that. So look at the idea here. If you have some numbers, yeah, for example, if I want to add these numbers this way, see here, 1 plus 1, okay, is 0, and then we have a carry here. Okay, so here in the first, so here I can make a circuit that can do this addition, and this circuit actually can be half other. So because here in the first one here, I just add 1 bit to 1 bit, and then I need summation and I need carry. Okay, so in the first one here, I can make one other for the first one. But starting from the second one here, I need to add 3 bits, 2 bits plus carry. The carry can be 0 or 1, right? So that is why the way we can do it here is this one can be half other. I'm going to tell you why it can be full other is okay. You can input 0, okay? But so let me go back to this one here. Yeah. So here, this one can be half other, okay? Or it can be full other, and then you can input 0. But anyway, forget it for now. So assume this is half other here this way. So this one, you actually can add these 2 bits, and then you have summation here, and then this carry is gonna be added to the next one. That's why you need a full other. Full other is gonna add 3 bits, as you see here. and then half other. Sorry, full other, full other, full other. So all what I need to have here, I need a circuit for full other to add 3 bits. The 3 bits are this bit and this bit, and the carry coming from the previous one. So, okay. So that's what we call full other. So the full other is used to add 3 bits. Okay, and by doing cascading, this is like you cascade it. Okay. By this way, this one is going to be very efficient. All what you have to do now, this one is going to add 4 bits to 4 bits. What if I want to add 5 bits to 5 bits? I'm going to add one more full other. What if I want to add 100 bits to 100 bits? I'm going to need 100 full others, okay, and another 100 full others. That's it. So it's going to be easy to extend it to any number of bits, okay? It's going to be very easy. So now we need what we call full other. So the difference between half other and full other, half other, as I have just explained, is used to add 1 bit to 1 bit, 2 bits. But full other has to be 3 bits. Okay? And so that's what I did here. Yeah. So that's what we call full other. Okay. So as you see here, we have you add 3 bits, you are going to get summation and carry. And as this is the truth table is here, you have 3 bits here. And then for everyone, we have carry and we have summation. And then similar to what we did before, okay, we're gonna do simplification using T-maps for the carry and for the summation. And then after that, that's what I got here. That's what I got. So that means it can be implemented this way. Okay, so this is for the carry and this is for the summation. Okay, and then also I told you this is for half. So number one, you should understand what we mean by full other. Okay, why we need it, because this is going to be the building block for the binary other. Okay, for more than 1 bit other. So then I here, because I want to put this one in XOR format. So I did some manipulation. After I doing some manipulation to this equation, I found this equivalent to this one. So if you have XOR with XYZ, so this one is equivalent to this one. I'm going to tell you why I did this one. Again, it's very simple. If you want to implement this way, it's okay. If you want to implement this way, it's okay. But I did it in XOR just to show you that full other can be implemented using 2 half others. Because half other already have XOR, as you will see, just to prove this one to you. But again, so, and then, yeah, that's what I proved here. So this is the original sum here. And then I just did some manipulation. I proved this one here is equivalent to XOR. That's what I did last time. And also, this is a carry, okay? Also, I did some manipulation to the carry so that it becomes this way. I'm going to tell you why I made this way. As you see here, this is a full other. So full other can be implemented using 2 half others and or gate this way. And now you can understand why I call it half other, because it's half of the full other. Because I'm saying, but anyway, just half of the full other. So, and here also I showed you here. So this is half other here, and this is another half other here, okay? And then we have X, Y. So if I go back a little bit here, yeah, this is for the summation. The summation should be X, XOR Y, XOR Z. And one way to do this one is, so I can input here X and Y, and then I get the output from here, I have another XOR with Z, this way. And that's exactly what I did. Look here. So what we did here, because this half other here, it has XOR. This half other has another XOR. See what I did here. So yeah. So here we have here XY. So this one X XOR Y. And then here I'm gonna input Z here, and then I'm gonna get here X XOR Y XOR Z. Okay, which is exactly equivalent to the summation. Okay. So here what I did here, I used the XOR inside the half other, the other XOR inside the half other to create the summation here of the full other. Is that okay? Let's come to the second one, carry. Yeah. So this is the carry as you see here, okay? The carry has to be this way. So as you see here in the carry, I need XOR, X and Y, and already I have this one here. So if you look at the carry, I already have XOR, XY from here, okay? And then I have to end it with Z. So we have Z here. We already have AND here. So I'm gonna use this AND here. So here I'm gonna AND Z with X, XOR Y this way. So the first part here, I'm gonna get it from here, the first part, okay? The second part, XY, it's already available here, XY. So anyway, all what I need, just add or get here. Okay. So let me tell you the conclusion here. The conclusion is number one, we have other to add 2 bits. Okay. And then we created full other to add 3 bits. And then I'm proving to you the full other can be implemented or can be created using 2 half others, as you see here, AND or gate. Anyway, so after that, I'm gonna use the full other as a building block to create any parallel other, okay, 4-bit, 5-bit, whatever. So something very important here, you may buy a chip. This chip can look like something like that. You have here C0. C0 is the carry of the first one, okay? Which is, most of the time you can make it 0. However, if you wanna, that's what I explained last time. So if you have this chip, if I wanna create 8-bit other, 8-bit using 2 4-bit. So if I have 2 from this chip, is that okay? And I wanna create 4-bit other instead of 4-bit. So I have 2 4. I'm gonna create 4-bit other. So all what you have to do is, so here I have this one is 4-bit. Another one is 4 bits, okay? And then the carry resulted from this one has to be input here. The first carry has to be 0. So this carry in the very beginning is 0. But this carry here has to go to the other 4 bits. You understand what I'm saying? So you can cascade. Very, very interesting thing, okay? Or very, very efficient. Any question? You understand this slide is very important. So now, as you see here, in order to create this other, I'm going to add these 2 bits. This is the result. This carry has to come here, and now I need to add 3 bits. This is the result, and the carry result it has to come to here. So as you see here, every time I do addition, the carry come here, and then I do addition for these 3 bits, and then the carry come here, and then I add these 3 bits together. The carry is going to come to here, and then add these 3 bits together, and this is the final carry, the most significant bit carry. Okay. Any questions? Okay. Now, in my opinion, this is one of the most interesting things in this course. That's my opinion. Why? Because as I told you in the first lectures, that the reason we are using 2's complement to represent a negative number is because it is hardware friendly. That's what I told you. It can be implemented by the hardware easily, and it's going to be shown here. So it's a good thing. What I'm doing here so because of the 2's complement, I can do other and subtract. So this circuit is very interesting. Why? Because this circuit can do other, it can do subtractor or subtraction for signed or unsigned numbers. So one circuit can be used for signed or unsigned number, other or subtractor. I'm going to tell you how. The idea is very simple. As I told you before, if I want to add A plus B, if I want to subtract, A take away B or A minus B, okay? So this actually, the subtraction is actually addition to the 2's complement. That's what I said. So A plus B prime plus 1. So this is how it is. You understand what I'm saying? So now you will see right now how this circuit, it can be used for both, okay? Addition and subtraction. Because subtraction is just addition, but addition to the complement of B prime plus 1. Because it's you will see right now. So the idea here is very simple. We have one input here. I call it M. Okay. If M is 0, this is other. If M is 1, this is subtractor. You can subtract. How? I'm going to tell you how. Okay. Let's start with the first one. If I put here 0, if M is 0, so this has to work as other. Okay. So remember this one, as I explained before, very important. If you have 0 XOR X, the result is X, right? But 1 XOR X is X prime. This is how XOR works. 1 XOR anything, you are going to get the complement of this input. But 0 XOR any variable, you are going to get the same variable. Okay, this is the main point here. So look what's going to happen here. So if I put here 0 here, so see how I made this circuit. So for A is connected to all of them directly. A is connected directly to all the 4 others. If you look at B, I'm not going to connect B directly. I'm going to connect the output of XOR, as you see here. So what is the main idea? The main idea here is, if M is 0, so 0 is going to come here, this one 0, this one 0, this one 0. And I have just told you, 0 XOR anything, you are going to get the same thing. That's why you can see here, 0 XOR B3, I'm going to get B3. 0 XOR B2, I'm going to get B2, and so on. So here, what's going to happen here, if you look at what I'm doing here, I'm going to add A to B, because if you look at the input of each other, you will see the input is B and A. So I'm going to add A to B, and the carry here is 0. So that's why it works as other. Let's look, okay, so if I want to use it like subtractor, so all what you have to do, I have to put 1 here, and that's what you are going to see now. So if I put here 1, look at the interesting part. So actually this one is 1, and here is going to be B0 prime, because this is how XOR works. 1 XOR anything, you are going to get a prime. Okay, so look what happened here. Here I input B0 prime, and then you add 1 here. You see what happened here? So what happened here, what this one is going to do is going to be A plus B prime plus 1. B prime, because you flip each bit, and this is B prime. You flip each bit. Also, you add 1 here, the one coming here. You understand what I'm saying? That's why this one is going to do subtract. Any questions? So you should understand the idea of cascading flip-flops to create other. And then now, using XOR, I was able to convert this other to subtractor, or the same circuit can be other with subtractor, reducing this bit. Okay. If I put here 0, we're going to have B here, B. If I put here 1, we're going to have B prime, and the 1 is going to come here. So it's going to be A plus B prime plus 1. And this is the main reason why I explained in chapter 1, I explained 3 ways to represent negative numbers. And I told you most of the modern computers are using the 2's complement because it is more hardware friendly. Any questions? Okay, now I want to explain this part here. So here, what I'm doing here, what I'm explaining is how I did 4-bit other and subtractor. Okay, I can control if the circuit is going to work other or subtractor for this bit. Also, I need to make overflow detection. You remember overflow, right? Overflow detection. After you do addition, I want to know if there is overflow or not. You get what I'm saying? Yeah. So that is why, in order to detect overflow detection, we have here carry, and we have what we call V. Okay, carry and V. The carry is actually the carry resulted from C4, and we have another same thing. I put here XOR. I'm going to tell you for sure why. So now I have two outputs, another 2 outputs, C and V. C is used in case of unsigned numbers to know if there is overflow or not. V is used if the numbers are signed to know if there is overflow or not. But why? I'm going to tell you quickly why. Okay? So again, I'm done with this part. Now I just want to focus on this part. So this part here should tell you if there is overflow or not. Okay. Now you should understand, or I already explained before what I mean by overflow. What I mean by overflow, when you add when you add 4 bit to 4 bit, maybe the result needs 5 bits more space. But here, the output I got, I'm gonna get because the hardware, this is hardware, right? So I add 4 bit to 4 bit, and the set is gonna give me 4 bits. Maybe I need more. Okay, that's what we call overflow. So let's start with overflow detection. And nothing is new here. This is similar to what I explained to you before about overflow. So it's very simple. What I'm saying here, in case I'm gonna take two cases similar to what I explained to you before. The first case is in case of unsigned numbers. Unsigned numbers, okay? Under unsigned numbers, I'm gonna talk about if you are doing addition or if you are doing subtraction, okay? Let's start with addition. So if I'm doing, which is this case here. Again, this slide is about unsigned numbers, okay? Now I'm doing addition here, okay? You wanna know if there is overflow or not, okay? Nothing is new. That's what I explained in chapter 1. All what you have to do, you have to add bit by bit, and then you have to look at the carry. So the carry resulted from the most significant bit, this carry. If this carry equal to 0, no overflow. If the carry is equal to 1, there is overflow. That's it. So this is similar to what I explained in chapter 1, but this carry here is actually C4 here. In this circuit, it is C4. This one, C4. The carry resulted from this one. So make it simple, make it very simple. If the numbers are unsigned and we are doing addition, if I want to know if there is overflow or not, check this one. If this one is 1, there is overflow. 0, there is no overflow. Okay? Now, let's take the second case. The numbers are unsigned. It's okay? Unsigned numbers. And now I'm doing subtraction, not addition, subtraction. How I can know? In this case, we don't call it overflow. We call it borrow, a borrow. Okay? So in this case, this is the second case here. So the second case here, in case of unsigned numbers, okay? And I need to know, I'm not gonna call it overflow. You will understand why, but I'm not gonna, it's not overflow, we call it borrow. You remember, when you do normal subtraction, we borrow, right? So for example, if you have 23 and you wanna subtract 9, okay? 9, can I subtract 9 of 3 from 3? You can't, right? So you need to borrow. I need to get 1 from here. And the one I get from here has, when it comes here, has to be 10, right? That's we borrow. That's what we call we borrow. Okay. So now 13 take away 9 is actually 4. You got what I'm saying? We do the same thing in binary numbers as well. Okay. If you do subtraction and you need to borrow to do the calculation, that's exactly what happens. So here again, I'm not gonna call it overflow. We're gonna, is there a borrow or not? Have you borrow or not? Okay, that's what you will see right now, what I mean exactly. So what I'm saying here, this is in case of subtraction. In case of subtraction, for example, 9 take away 3. 9 take away 3, the result is 6. There is no borrow. So if you don't borrow, if there is no borrow, that means the carry is equal to 1. Okay? So, but if you borrow here, so look at this example. 3 take away 9. Is that okay? In this case, there is a borrow, you borrow, okay? And in this case, the carry is equal to 0. Okay, but in this case, I got 10. Is that how? So why I got 10 here? This is the most important thing. Look here. So 3 take away 9, I got 10. Okay. So what happened is you here, because this is 4 bits, right? So this 4 bit is gonna borrow. When you borrow after 4 bits, anything you borrow is gonna be 16. Okay. Similar when you borrow from here and it becomes 10. Same thing, because this is 4. So what happened here is actually because you borrow, how I got this 10? So this 10 is actually 3 take away 9 plus 16, which is the borrow. You got what I'm saying? So the answer I'm gonna get here is a correct answer, but after you borrow. You got what I'm saying? So here, that's why I added 16. So this 16 after you borrow. So all what I need to know here in this case, again, I'm gonna make it very simple. Here I'm talking about number 1, unsigned numbers. Number two, I'm talking about subtraction. You need to know if there is a borrow or not. Okay. So all what you have to do, look at the carry. If the carry is 1, it means no borrow, and the result is perfect. Everything is okay. If the carry is 0, it means the result also is correct, but after you borrow. That's why you have here 16. Because you borrow. So there is some borrow. Okay? Any questions? So in both cases, if you want to know if there is overflow or if there is borrow or not, who's going to help you? The carry. But in case of addition, if the carry flag is 0, it means there is a borrow. But if the carry flag is 1, it means no borrow. So 1 is okay in this case, means no borrow. One more thing here. Here, the result I got is wrong. Okay? Because I need one more bit. The result I got here is correct, but after I borrow. So here 16 is added. So it's like you added 16 plus 3 plus 9. And here it is 16 because this one is 4 bits. Okay? If it is more than 4 bits, so what you are going to borrow is going to be greater than that. Okay, similar to the decimal number. So if you have here, whatever I'm going to borrow here from here is 10. But if I borrow from here to here, it's going to be 100, right? And so on. Sorry, you also borrow here. You borrow 10. But the weight here, because this one is in tens. So here, because this one is 4 bits, so anything you borrow from here is going to be 16. Okay. Anyway, so now let's come to in the case of signed numbers. So here, how I can know if there is overflow or not here in this case? Very simple. Just don't look at C, it is V. That's it. So if V is 1, that means there is an overflow. If V is 0, there is no overflow. How? As I explained to you before, how can you know if there is overflow or not? Okay, as I explained to you before, in case of signed numbers, this is what I explained to you before, right? If you add 2 positive numbers, so if you add 2 positive numbers, result in, I'm sorry, I'm going to put it this way, result in a negative number, okay? And here you add 2 negative numbers and you get a positive number. Is that okay? I'm sorry, I'm going to put it this way. So overflow can happen only in these 2 cases. Is that okay? So add positive to positive, you got negative. Add negative to negative, you got positive. Okay. If the sign is different, if I add positive to negative, no overflow because the number is not going to get bigger. Don't think about it. Okay. So overflow can only happen when the 2 numbers assist each other. Both numbers are positive or both numbers are negative. Is that okay? So I'm going to correct this one. So this one negative and this one is positive. Okay. So these 2 rules are equivalent to this rule here. Look here, they are the same. Here, in order to know if there is overflow or not, I need to observe the carry into the sign bit and the carry out of the sign bit. Okay. If they are different, if these 2 carries are different, that means there is an overflow. Okay. So this, I'm gonna prove that to you. What I'm saying is that these 2 rules are equivalent to. I'm gonna look at this is the sign bit is here. I'm gonna look at the carry coming to the sign bit and the carry getting out of the sign bit, the last bit here. Okay. So if I want to know if there is overflow or not, I need to look at this carry. Also, I need to look at this carry. Very simple. If these 2 carry are equal, if C4 equal to C3, right? That's what I'm saying here. If these 2 carries are not equal, that means there is overflow. So if these 2 carries are not equal, so there is overflow. Okay. If these 2 carries are equal, so no overflow. Okay. So who's gonna give you 1 when they are not equal? XOR. That's why I put here XOR. Again, what I'm saying is very simple. If I want to know in case of signed numbers, if I want to know if there is overflow or not, very simple. If these 2 bits, okay, are not equal, so one of them is 0, the other one is 1, that means there is an overflow. Which gate it's gonna give you 1 when they are not equal. So that's why here I put XOR, so that this should give me 1 when they are not equal. Okay. The last thing here I want to explain, and then we are going to start the test, is, okay, wait a second. In chapter 1, I told you when you add 2 positive numbers, you get a negative number. That's overflow. If you add 2 negative numbers, you get a positive number. This is an overflow. And in this chapter, you are telling us these 2 rules are equivalent to this one. Look at the last 2 cards. Okay. Look at the last 2 cards. If they are not equal, that means there is an overflow. Okay. So here I try to prove this one to you. So maybe I'm gonna do it next time, but here I'm trying to just to prove it to you, to show you if each time here I compare if there is a carry coming, carry out, and then anyway. So I'm gonna do this one next time. So let's start the test.